As you might have noticed from the topic itself, it says some cute concepts. So these, see, till now we discussed about generally the trusses, and we saw how the method of joints, method of sections can be used to investigate or analyze a truss. But then in that segment I could not cover up some very interesting topics which are in a way like some tricks also, but if you use them, it's very easy and very fast to solve some complex trusses. And so that, but and then these are very cute concepts, so that is why I separated them out in a separate segment, and I have named them some cute concepts. So the first one of those things is about the zero force members. Okay. Now what these are? See, the thing is, we discussed that when we analyze a truss under some loading, all the members are two force members anyways, but then they will have some compressive force along them or some tensile force. But then it is also possible that it may so happen in a particular condition of loading that some of the members will not have any load, right? Because if compression is also possible, tension is also possible, then in between value, that is 0, also is possible. So then as if that element is not even required for the if you remove that element from the truss, still the truss will be in balance. But then why would we have such elements in a truss? The thing is, sometimes as I said just now, that under a specific condition of loading this may happen, but if the loading condition slightly changes, then that member may not remain as a zero force member, and if we actually physically remove that element from the truss, it may fail, the whole truss may collapse. So that is why we can't just remove the member if for a given loading condition it is a zero force members. So but in analyzing a truss under a given condition of loading, it's quite useful if we can recognize these zero force members just by inspection, visual inspection. Now, so that is what we are going to discuss in this segment. Now the first, there are two conditions basically when you can visually simply tell that the forces in the members are 0. Okay. One of them is like this. So I'll say this is case 1. Case 1 is when you have two members. Say this is one member and this is another member. They are connected at this point and there is no external load applied at that joint. Okay. Then we say that both these members, let me give some names to them as well. Say this is A, B and C. So that means AB and BC members. So both in this case, if this condition is very important, if that no external load is getting applied at that joint, okay, then both FAB is equal to FBC is equal to 0. So if in a truss under a given loading condition, whenever you see such a portion or a segment, you can simply tell that these are 0 and you can remove them for analytical purposes. Okay. So that is one. And the case 2, okay, let me write here. Case 2. Case 2 is like this. Suppose you have one element like this member, another member say is like this, which is collinear, okay, with the joint here, and then you have an additional member which is something like this maybe. Okay, let me give some names to them. Say A, B, C, then D. Now, if that is the case, there are two members which are collinear, then there is another member which is having some angle with that. That angle could be anything. Then, if there is no force, so that should I mention somewhere, because that's very important. In both the cases, no, I'll say external force is applied at B. That's important. Yeah, so here also, in both the cases, here also and here also, no external force must be there. Then here we can say that F dB is equal to 0. That means dB is a zero force member. Now why so? So these are the two cases in which you will get zero force members, but then why so? The reason is very simple to see. Let's see, suppose this condition is not valid and there is some force in one of the members, then if you resolve the forces, let me show the forces like that. Suppose this is a force, actually I have drawn them almost 90 degrees, so anyways, so this suppose is FAB and say this is FBC. Now if you take a coordinate system which is say in this direction and it has got so this is X and this is Y, then see the thing is this FAB will have at least some component in this direction, okay. In fact, the way I have drawn, it's almost like the full force is in this direction, but even if it is in some other angle, a small component will be there in this direction, right? A small component. Even if it is the theta is very small, this theta I am talking about, if this theta as small as possible, even if it is there, then you will have a small component in this direction, but then there is no other force to balance that thing. If you consider the equilibrium of this point B, in this direction it can be balanced by this force and the component of FAB in this direction, but what about the vertical component? So then there is a problem. So that is why the only and then similarly if you consider so from this you say that FAB is 0. And similarly, if you take a coordinate system which is aligned, whose x-axis may be aligned with this, and if you resolve its component, FBC's components, and then you can show that FBC must also go to 0 for very similar reasons. Okay, and that is why both of them must go to 0. So that's the reason why under such conditions both of those member forces will be 0. Now coming here, very similar reasons, you just define a coordinate system maybe like this, x and y, okay. Now if you have a force here, say FBD, right. Now FBD and say so the forces here are say FAB and on that side maybe the force is FBC. Now the horizontal components or the x components can be balanced. The FBC's x component and FAB's x component and FBD's x component, they can balance each other. But what about the component which happens in this direction of FBD? There is nothing to balance that, because we have said that there is no externally applied load at point B. So then this point cannot be in equilibrium, and that is why the only possible case is that this must go to 0. Okay, so that's why under these two conditions you can simply tell that the zero force members you can simply visually inspect and tell, and then once you recognize the zero force member, for analysis purpose you can simply remove them from the structure, okay, or you just assume that they are not there and then simply analyze without them in the structure. Okay, so that's one of the concepts. And then the other one which I was a similarly acute concept, for example, like this. Suppose you have a member like that which is co-linearly connected to another member, so like this, and at the same location suppose you have two more members which are crisscrossing like that, okay, and say this, okay. Now at the same location everything is connected, and these two are collinear and these two are collinear. Then let me say give some names to them, the forces. Suppose this is F1, this is F2, and say this is F3 and this is F4. Now under such conditions you will have to have that F1 is equal to F2 and F3 must be equal to F4. Okay. Now, so the reason, if you want to see the reason, the same situation means, or the same way of analysis that we did for the previous case, you can do it here. Let's say we think of a coordinate system like that, which is perpendicular along this line, that is F3 F4 line, and so here say y axis, this is x axis. Now and think about the equilibrium which is caused by these forces F1 and F2 in the y direction, okay. Now that will tell you that F1 must be equal to F2, because these two have no components whatsoever in that direction. So then only thing which have to balance is this, and because the angles are exactly same, these being collinear, so F1 must be equal to F2. Similarly, if you take a coordinate system, say x dash y dash, which in this direction, say this is x dash, and say y dash is in this, y dash and x dash. So now if you resolve the force components in this direction, you will show that F3 must be equal to F4, okay. So that means these are the conditions which must prevail under such conditions. So this is the second thing which I wanted to talk about, and there is a third concept which I am interested in this segment, and that is about determinacy, okay, whether a system of truss is statically determinate or not. For that there is something called internal, sorry, I'll use the green one, say internal or external redundancy. Now what it means is, let's first talk about external redundancy. That means if you have a truss, something like that, could be, okay, whatever, and then you have some supports, okay, and now in this case, and let me put another one here, could be say like this, okay. Now if I create many supports which are not necessary, this redundancy means actually that they are unnecessary, redundant, useless, means they are there, but without them also things can work. So the same thing in this context is like this. There are supports which you have used which are not actually necessary. Even if you remove some of them, the system will still be stable, okay. So for example, in this case, if I remove this complete whatever that is, the support, the hinge support, still it will be balanced, okay. The system will stay balanced. Similarly, if I remove this, and then also the system will be balanced, but then still there is some redundancy or additional things which can be still stripped off from the structure. There is this hinge support. I can still make it a roller support, thereby reducing one more constraint from the system, still the system being balanced. So that's what is called externally redundancy. So to check that, you just think about whether you are having some additional or extra support from the ground, okay. Now we know that three ground reactions can be evaluated, isn't it? If it is a 2D plane truss, so three unknowns you can evaluate from the equilibrium equation. That means at most you should have such supports from ground, so that maximum three kinds of reaction forces will come. Then the system will be externally not redundant. If there are more than three reactions which are coming from the ground, then definitely it is externally redundant. Then what about internally redundant? Internal redundant means again you have some members which if you remove also the system won't fall. For example, say I have, this will be a stable structure, but then if I also join like this members, okay, I put two more members like that, and then just see that here they are, means overlapping, they are not crossing each other, or they are not joined at each other, okay. So let me put the joints here to show that where all joints are there. Yeah, so those are the joints, but the other places they are not. But then if I remove these, say either this yellow or this green, still the system will not collapse, it will be stable. Now these are called internally redundant members, okay. So that means in the structure internally there are more members than necessary. So in both the cases, so we are basically talking about the necessity condition, how many supports are necessary, and if you have more than the necessary number of supports, it is called external redundant, and if there are more number of members than are actually needed for stability, then they are internal redundant. Then the most important thing which I wanted to talk about this is, for a structure which is not externally redundant, okay, that means you have only three unknown reactions which are coming from the ground, okay, or three reactions which are coming from the ground, then just think about how many unknowns you have in all. These three are the ground reactions, so three ground reactions, and then suppose m members are there, then for each member you have a member force which is an unknown, okay, which you actually desire to evaluate when you say analysis, okay. And then how many joints? Say J is number of joints, Okay. Then, so these are the unknowns, isn't it? So these are unknowns. And how many equations you can write with J joints? For every joint you saw that two equations, that is for equilibrium of every joint, we wrote in the method of joints, we saw that two equations, fx summation of fx equal to 0, summation of fy equal to 0. So like that two equations we were writing. So number of equations are 2j. So that means if you have m plus 3 is equal to 2j, then you can solve for all the unknowns properly, because these are the number of unknowns, these are the number of equations, and if they match you can solve them exactly. If you have means more members, then so that means this side is more than that, then obviously you have redundancy. And if you have less members than what is desired, then obviously it will collapse. This is just a necessary condition, okay, this is not sufficient. That means you can't just say that if this condition is satisfied, obviously the truss will be stable. It's not, okay. You can always arrange members in a very bad way, so that still with sufficient number of members you have a not stable structure, okay. So that means this is a necessary condition, and if this is required for your system to be stable. So this needs to be kept in mind. So that was it. So these are the three things which I wanted to discuss under this segment of CUTE concepts. One is about the zero force members, the two ways in which you can visually inspect and catch them and remove them. And this is one where you can just from visual inspection you can write some equations directly. And this is the external and internal redundancy and the statical determinate condition. So this is the condition of a truss to be statically determinate, where externally no redundancy is there. So that's it. So we can stop here for this segment, and in fact this finishes the truss portion, and we will see in the next segment.